All right, kids, now we are on to the real meat of this unit, which is proving identities. So proving means you are given an equation, and usually when you're given an equation, you assume equality, but you have to prove equality. Okay, trig identities. So here's my strategy, right? And just because I purposely didn't number these, because I don't necessarily just do 1 and 2. I do this one is the first for a reason. I do look at both sides of the equation, and in general, I start with the more complicated, what's got more stuff going on. One side's a fraction, one side's not. I usually start with one side of the equation. And then I use my identities list to kind of sort of simplify, right? Which is what we learned, what we did in the previous video. I kind of simplify, AKA rewrite one side. I typically try to write into sine and cosines most of the time. Sometimes I combine fractions, sometimes I split them up. Oftentimes factoring, your algebra 1 factoring, difference of two perfect squares, perfect square trinomial, all of those patterns, your x squared minus y squared pattern, your x squared plus or minus 2xy plus y squared pattern. Those patterns matter. Multiply by a convenient one. I showed you that in a simplify, right? An example in the last video. Stay on target, right? Good old Star Wars, stay on target. Don't forget where you're going. Always, whatever side you pick to start with, always keep in mind where you're going and what you want to see. You must work on both sides individually. If you start on the left side of the equality, don't do anything to the right. If you start manipulating the right side, don't touch the left side until you're done. Remember, it's confusing because in all of your algebraic career, when you're given an equation, you can do whatever you want to one side versus another side, but you're not solving an equation. You are trying to prove that one side is equal to the other side. Okay, and that's sometimes a hard thing to cement in students, right, in their psyche as they start these problems. So all I can do is just show you a bunch of these and just do a bunch of them with you. All right. Each time I've shown you, I've picked just problems from the book because we'll assign some, but just do a bunch of them, pick extra ones. So again, the idea behind this proof is that even though I've written the equal sign, you need to think, I'm not sure the left is equal to the right. Now, that's not really true. They are equal, but your job is to prove that they're equal. So that's why I put a question mark here, because you don't want to just multiply both sides by 5, multiply both sides by sine. No, you want to make yourself a wall. Make a wall and start on one side. I must say that my tradition is to start on the left side. That's just my habit, right? Unless the right side is so very complicated. But when they tend to look kind of sort of the same, I generally start with the left, but there's no reason. That's no reason. That is just my convention. So I look at both of the sides, and I notice that both of them have sine in the denominator, but the second denominator has 2, has a sine squared. So look at what I chose to do first. What does it look like? I took secant squared minus 1 and I used an identity to change it into tangent squared. Why would I do such a thing? Can you imagine why I would do such a thing? Remember, I'm trying to match the right side. I went from secant to tangent. Why would I do that? Because tangent has a sine in it. Tangent is sine squared over cosine squared, and then times this 1 over sine theta. Did you see what I did there? How did that happen? Oh, this is sine theta times sine theta. And since those are 2 factors in the numerator, and I have 1 sine theta factor in the denominator, cancels out, and I'm left with just a sine over cosine squared. Why does that help? Oh, snap. Cosine squared, my Pythagorean identity, is the same as 1 minus sine squared. Oh, Lanta, I matched the right-hand side. I am done. There's my QED. This is really what QED, usually they do this. Boom, boom, QED is the tradition. I don't know why. I did look it up. Quod erat demonstrandum. That's me trying to talk Latin. And it means, thus it has been demonstrated. I have shown this to be true. I am so fancy. QED. Let's do another one. Prove. So the minute they say prove, remember, you're questioning whether the left equals the right. So draw yourself a wall and don't touch. When you start changing one side, don't go across your wall until you match. So again, those look to me to be, one side doesn't in particular look necessarily more complicated than the other. So I just tradition, start on the left side. And then it's just my tradition. You don't have to do it. What is happening right there? What did I do? What the heck is that? What is going on? Can you tell what I did? Piece by piece? I didn't know what to do, right? I've got a tangent squared and a sine squared separated by a minus, and I have a tangent squared and a sine squared over here as a product. I don't know what to do. But I saw a fraction, so I started to think about, well, I'm sorry, I didn't see a fraction. I saw a minus sign. I need a common denominator in order to make that subtraction into one term, right? To one term. So I turned tangent squared into sine squared over cosine squared. And then what did I do with this? How is that legal? This is a 1. Cosine squared over sine squared is just 1. So I multiplied sine squared by 1 in order to get a common denominator. Now, what are you going to do when you have 2 fractions and a common denominator? Put everybody on the same numerator, right? In the same numerator. Over your common denominator. Now what am I going to do? Factor. Factor a sine squared out, and you get 1 minus cosine squared, right? Do you see that? Factor the sine squared out front. How does that help? Well, what is sine squared over cosine squared? Oh, snap. And what's 1 minus cosine squared? Oh, snap. I think I'm done. I matched the right-hand side. QED. Done, baby. I feel so accomplished when I'm done with these. I don't know about you. But I think you will feel the same. Or maybe not. Let's do another one. All right. Remember, with the word prove, you're questioning. I mean, not really. They're going to be the same, right? But you question and draw a wall. Start on one side. My habit, start on the left unless the right side is very complicated. Just my habit, though. So what are some things I'm thinking about? All right. I noticed that I have a fraction on one side and on the left, but I noticed that the fraction on the right side is a sum, and I only have one term in the fraction on the left side. So what did I choose to do? See what I did? This is a convenient 1. I didn't have any squares. You can't square the numerator and denominator of a fraction, right? 3/4 is not the same thing as 3 squared over 4 squared. They are not the same. You cannot just square the numerator and square the denominator, but I can multiply anything I want by 1. And since I couldn't figure out anything to do, no factoring, right? No identities because I don't have any squares. So I multiplied by 1 because I know I need 1 plus cosine x in the denominator. So I put 1 plus cosine x in the denominator, but in the numerator as well. And then, hey, what is this? 1 minus cosine x times 1 plus cosine x. That's the difference of 2 perfect squares. Crazy, right? And now what do you have in your numerator? Sine squared, right? Here's one of your Pythagorean identities. That's sine squared. What's in my denominator? Notice I did not multiply it through, because what's going to be true now? Sine squared is actually sine x times sine x. 2 factors of sine x in the numerator, 1 factor of sine x in the denominator. Bye-bye. And, oh snap, I matched the right-hand side. And I'm done. No, you don't have to write QED. You just have to write the right hands. Right, what I would normally do here, what equals, I wouldn't write RHS. I would actually write the right-hand side, noticing that I haven't changed it at all. Now, I am not saying that there aren't some times where you do manipulate both sides, but it will get messy quickly if you do. Sometimes the proof gets out of hand. So always default to picking one side and manipulating it only, and only defaulting to changing the other side if you get stuck. Because I'm telling you that oftentimes it leaves you down a rabbit hole and you'll never resurface. Let's do another one. Oh my gosh, what is happening in my life right now? I think I'm going to start on the right-hand side this time. Do you see why? The right-hand side is just devastating. Now, notice this is a product. It's a product of 2 things. It's a product of 1 big factor and 1 small factor. But look at my first group here. What can you factor, good F word, what can you factor out of that first red group? There's a whole bunch of freaking cosines on, isn't there? How many can you factor out front? 2 of them, right? Take 2 cosines out of here and you're left with 1. Take 2 cosines out of here and you're left with 2. Take 2 cosines out of here and you're left with 4. Now that doesn't seem to make an awful lot of help. Notice I had 2 factors and now I've got 3 factors. But I want you to focus on that middle factor. And I want you to think algebra 1. What is x plus y squared? No, What is x minus y squared? What do you get when you have x, one thing minus another thing, and you square it? You get x squared minus xy doubled plus y squared, don't you? Doesn't that look kind of similar up here? Oh, wait a second. There's squareds and a force. Well, look at that factoring of a perfect square trinomial. How do you factor that? X is squared, x times y squared, but with a minus and doubled, plus y to the fourth. That's all this is. But if your algebra isn't strong and fluid, you won't recognize that. But it is just an algebra 1 perfect square trinomial. That's all it is. 1 minus cosine x squared, all squared, is 1 squared minus 1 times cosine squared doubled plus cosine squared squared. Oh my Lanta. But if your algebra, if you haven't done these two kinds of things 500 times over and over and over again, you don't recognize, your brain doesn't make that connection. Now I've shown it to you. Now you have to focus on making your brain make that connection. Look for perfect square trinomials. Okay, let's go on. How does that help? What am I going to do now? Can you see? What did I do? Inside this parenthesis is a Pythagorean identity. It's sine squared. Now I have sine squared, but that's all squared. So what is this? Sine squared squared is sine to the fourth times another sine x is sine to the fifth. Sine fifth, sine x to the fifth, and then I have cosine squared out front. Check, check, I matched the left-hand side. Oh my gosh, I feel so good about myself. I think I'll show off and throw out my Latin. All right. So just a bunch of different examples, doing a bunch of proofs. In our live session, we'll do a bunch more together. And you can't get good at doing these proofs without just doing a bunch of them over and over and over again. And oftentimes you have to look at the solution and work backwards. That's how you learn with these. That's okay. All right. No one is just, this isn't natural for anyone. But the stronger your algebra 1 and algebra 2 mental manipulation, you don't have to write it out, the easier these will be for you. Okay. All right. I will see you in our next live session.